Welcome to qnawire.
In this problem, we have a steam power plant again, the reheat regenerative Rankine cycle. Let's see here. So we got, it's best to probably just walk through the schematic here of it. I drew both turbines as one. You could either say that this is a low pressure, or high pressure, and then there's a low pressure afterwards, and then they're connected by the same, to a shaft. But I just drew them as one, and just assumed that we kind of had a bleed. So what we have here, let's say we start at one, we go through, we pump it up, pump the water out of the condenser up to a pressure of, let's see here, 800 kilopascals. It goes into this open feed water heater, and we mix it with some of the steam we took off, or came out of the high pressure turbine. And so we mix that in this open feed water chamber. Then we take that and we pump it back up. We pump it up to the pressure, the boiler pressure, which in this case is 10 megapascals. And we then boil it and we feed it into the turbine. And some of the steam that we take out of the high pressure turbine. Actually, let me just put a line in here so that it makes things a little bit easier to see. Let's put it right here. So there's like two turbines. So we take some of this that's coming out of the high pressure turbine, the steam, and we heat it again. We throw it back into the boiler.
USD has moved down to 0.173 over the last
And we have, let's see here, we have it then coming back and being fed into the
USD has moved down to
the low pressure turbine. There's also basically there's you could see, is all of it the steam? There's some steam at this pressure to feed the feed water. The rest of the steam is reheated to and is expanded in the low pressure turbine. Yeah, so then I guess we take it all out of here. We take it all out of here, reheat some of it, and then help some of it here, and then feed it back into this. There's nothing coming, there's no direct connection here. So these are really two separate turbines, and I guess I should have really drawn them as that. But anyway, then it comes out and it goes in the condenser, and we get heat out. So we have work from the pumps in, work from the turbine out, heat in the boiler, heat out at the condenser. And so we're told that we have 800 or 80 megawatt cycle here. Temperature here is 550 degrees C. Low pressure side here at the condenser is 10 kilopascals. And we have quality factors of 1 at here and at here. So we have condensed liquid here, both of these states. So let's see here. We can get the enthalpy and specific volume at 1. So we can get the power that is being put into the pump 1. And then we can get the enthalpy at 2. Enthalpy and specific volume at 3. We can get that. We have enough information to get that. And then we can get the work put into the pump 2, which is 10.3 kilojoules per kilogram. And then we can get the enthalpy at 4, which is just this plus this from energy balance on the pump here. Now we can find the enthalpy at 5 because we know the pressure and temperature, and we can get the entropy. We know both turbines are 100% efficient, so the entropy at 6 is the same as entropy at 5. And that allows us to get the enthalpy at 6. We can get the enthalpy at 7 because, let's see here, we know the pressure at 7 is the same as the pressure at 6, right? And what else do we know about 7? let's see here. What did I, again, I didn't copy everything completely from my notes. So let me see how I got, what I used to get that. Just trying to condense these problems a little bit because really, if you work them all out like without redoing them, there is a lot of pages of work that I'm leaving out here. But oh yeah, at 6. Let's see here. At 6, did we say it was a saturate? Wait a minute. Is this the right problem? No, that's why. Let's see here. Oh, this analysis is lengthy. Okay, so 6. We know, no, 7. We know the pressure and the temperature at 7. Did I not write that down here? That's probably why I can't find. Yeah. At 7, they actually told us some information there. T7 is 500 degrees C. That's why I couldn't find the other piece of information. So 2 thermodynamic properties at 7. What were they now? We had 6. And so 7, we had, yeah, we had pressure and temperature. But basically, we could have got that anytime we wanted, right? We had pressure and temperature at 7. All right, so we get enthalpy at 7, entropy at 7. Entropy at 8 is the same as the entropy at 7. That leads us into the two-phase region at 8. So we can get the quality factor is about 96.3%. Find the enthalpy there. And now we have the enthalpy at every point we need, so we can start looking at different pieces of this system. First thing we can look at is the feedwater heater. All right, so let's see here. This is stuff going, enthalpy flowing into the feedwater heater, enthalpy flowing out. We divide through by M3 and define Y as M dot 6 over M dot 3. M dot 3 is actually the same as M dot 5. So this M dot 3 is actually, you know, the flow going, the rate of flow going into the turbine. So this is kind of the amount that is coming out at 6 relative to 5. So we do have some flow from here to here, I think. Because not, oh no, yeah. All of the flow isn't going through here. So that means there is some kind of, if we look at this as 2 turbines, then we have coming out at 6, we have some going into here, and then we have some, so there is flow crossing this boundary because 6, the flow at 5 and at 6 is not constant, so there's flow over this boundary here. So let me actually put in a little flow arrow there. All right, so let's see here. Where are we? All right, so that allows us to find Y, and so that winds up being about 20%. So about 20% of this goes out of here, and then comes back in and gets pumped back into here, and some of it goes into here. All right, and then the rest of it basically continues down or into the low pressure turbine, or either we can think of this as a bleed with a kind of another input here, or we can think of it as 2 turbines where we have some of it, yeah, either, you know, pipe directly from the output of the one into the input of the other. Anyway, I'm not sure exactly how they would do that in practice. Probably have 2 turbines because you can probably make each one a little more efficient based on knowing the the pressures in it. So a high pressure turbine might be designed a little differently than a low pressure turbine. So you'd probably have two different turbines and then just have feed the output of one into the input of the other. Okay. All right. So now we can figure out the heat transfer in, which is just H5 minus H4. Get that value. Heat transfer out. We have simply, this is H8 minus H1. And so that's a simple one. And we also remember we need to multiply this by 1 minus Y because not all of the flow is going through this condenser. Some of it's coming out here. So 1 minus Y of it is going into the condenser out of the fraction of what's going into the turbine. So we have 1 minus Y times H8 minus H1. The net work is this minus this. So with the net work, specific work, and the net power out, we can figure out the mass flow rate, and that winds up being 54.5 kilograms per second. And likewise, we can find the efficiency, either the simplest way is this divided by this, and that winds up being 44.4%. So pretty efficient from comparing to the other systems we've analyzed in here.